Okay, so we are back. We're doing new material, downloading some couple of lectures, one for today, Friday, and then one at least one over the weekend as well. And we're going to start going on ring theory. So yeah, we did had a good go at groups, abelian groups, non-abelian groups, Silo theorems, some finite group stuff, symmetric groups, all that good stuff. And now we're gonna move into the next part of algebra, the big section of the course called ring theory, which is going to be the end of the course now, obviously, because the semester's getting close to being over. So let's start with the definition. A ring is a set R with two operations, plus and times, right? So a group has one operation. Now we have two. And satisfying one. So R along with plus is an abelian group. Operations, by the way, here are binary operations. So I didn't say that, I just said two operations. Well, what does that mean? Well, they're operations maps from R cross R to R. So two ways to input two different things and spit out one thing. Okay, I mean, they're plus and times, so they mean kind of what you think they mean. So R with plus is an abelian group. Multiplication is, number 2 says multiplication is associative. So A, B, C is A, B, C for all A, B, C in R. And number 3, the distributive law. So A times B plus C is equal to AB plus AC. And B plus C A is BC plus BA. Okay, so that's a ring. So most of the time you demand more things. So I'll say for R is unital if there exists an element 1 in R such that 1A is A, 1 is A for all A in R. Right? So of course you could live without that, but you don't want to typically. So typically we'll always demand that. There are, yeah, so Goodman actually has a nice little section here where he points out that there are rings, there are interesting rings that don't have the identity element. In particular, if ever in your life later on you get into functional analysis, there are rings that occur there called operator algebras, which are very, very large rings and most of the time don't naturally have identities. Personally, I always like an identity, although in my research in math I have encountered non-unital rings. They always make me admittedly a little uncomfortable, but okay. Sometimes sometimes they do come. So okay. So that's just something that's not really part of the course per se. It's just something to say. We will basically always demand this. Okay. So the unit of the abelian group in particular is called 0. So let me remark that the unital means that there's this 1. So that's a multiplicative unit. On the other hand, R plus is an abelian group. So the unit for plus is called 0. And that always exists. That has to exist because R plus is an abelian group written additively, right? So by the axioms of abelian groups, there's a additive unit and additive inverses. So we can talk about 0 and negatives and all that. Okay, the unit for plus is called 0. Yeah, exactly. So rings will always have 0 and they will almost always have 1. Although Goodman is right to point out that shouldn't technically be in the definition. Okay, so there's a few easy properties that you can deduce. Let me say that one useful fact is that it's always possible to multiply by an integer in a ring, right? Because you can take 1 plus 1 plus 1 plus 1. So let me just further remark. For n in Z, we denote NA by A plus plus A, right? Which is equal to, right, this is one way to denote it, but it's also, of course, 1 plus 1 plus 1 times A by the distributive law. And this is the same as A times N. So there's always kind of a way to think about integers as being inside, well, being inside your ring would be wrong. There's always a way to think about integers as kind of acting on your ring, you know, via multiplication, because I can always take that element. This is for a unital ring now, which is, again, unless I say our ring is not unital, I will always assume that. So as long as you have this 1, you can talk about natural numbers, kind of. Natural numbers and integers. So this remark with plus would be, this would be for n in z, n greater than 0. So let's slightly correct that. For n less than 0, n times a is minus a, minus a, minus a. And remember, our plus is in abelian group, so it makes sense to talk about plus and minus. There's an additive inverse. They mean exactly what you think they mean. Okay, so all right, so that's good. Let me make a further definition on this definition. R is commutative if A times B is B times A for all A, B, and R. So again, the addition always commutes because R plus by its very definition is an abelian group. The multiplication need not commute. So let's look at examples. So what are some naturally occurring rings? We've encountered a lot of them. So R is Z, Z mod N, Z, Q, R, C. And finally, let me give you a more interesting one, N by N matrices over any field. So I'll just say F, where F is any field. Right? So on all these, we know exactly what all the operations are, plus and times. Let me say what they are. What are the operations for N by N matrices? So what are the operations there? Let's see. Different page. So in M in mat N by N of F, we have A plus B is sum of matrices A times B matrix multiplication. Okay, so it's no surprise. It's not. I realized that as I was saying that, it made it sound like it was some kind of interesting new thing. Of course, it's not. We know how to add and multiply two matrices. So you know, there's no doubt about what the operations are supposed to be here. But I just wanted to say it explicitly. It's odd. My camera's kind of doesn't seem to be resolving very well on the text here. Sorry, give me a sec here. I don't know why. Usually this kind of focus should be completely automatic. There we go. Sorry about that. Okay, so A plus B is just A plus B, the sum of matrices. A times B is matrix multiplication. All right, we'll revisit this. We'll revisit this later. Note that this is a ring that's not commutative. So the first set of examples I listed, Z, Z mod N, Q, R, C, these were all commutative rings, right? The multiplication is commutative. Here, the addition is commutative. That's an abelian group, certainly, if I can add two matrices in any order. But A times B, not equal to B times A, as always. Okay? So this is an interesting non-commutative ring. Very interesting one. Okay. Let's give another definition. Very important. A field is a commutative ring in which every non-zero element has a multiplicative inverse. Okay. So a field is a ring in which you can divide, right? Okay, so you probably have heard the word field before, precisely because of linear algebra, right? And in 416, they say, well, let F be any field. And they say, what's a field? Well, it's always, for us, it's always going to be R or C, or maybe occasionally Q, and they don't really go beyond that. But of course, in the broader mathematical world, there are many, many fields, and we are interested in lots of them. So, that's the general definition. It just means that you have division, right? You have every non-zero element you can divide by it. You can multiply by its multiplicative inverse. Okay, so in particular, the set of non-zero elements in a field form a group, an abelian group under multiplication. So if F is a field, F cross, which is F and F such that F is not equal 0, is an abelian group. Right, and we've used this a bunch of times. We've used the fact that non-zero real numbers form a group. We use the fact that that non-zero complex numbers form a group, an interesting group that has subgroups, which are like the circle. That's a subgroup of C star. What's C star? The group of non-zero complex numbers. Well, C is a field, so that's why that's a group. Okay, so all right, so let's do so we've already seen a lot of interesting examples of these things. Let's do an additional example here. So clearly, I'll just say clearly, by the axioms, Q, R, C are fields. Okay, that's fine. But now let's claim, we have the following claim, that Z mod NZ is a field. That happens if and only if n is prime. Okay. We proved this already back in week 2 or 3 of the course, very early on, in different language, right? So what does it mean to be a field? It means that every non-zero element is a multiplicative unit. Now, what are the units in Z mod NZ? So we characterize them. So let A be in Z mod NZ, right? So this A is a unit. So we proved long ago that A is a unit if and only if what? Well, A was a unit in here if and only if A is congruent to, if and only if A and N are relatively prime. Right? And this had to do with, the definition of relatively prime, right? There exists some B such that AB plus 1 is a multiple of n, right? So that was one. We had a couple different characterizations of what it meant for two numbers to be relatively prime, and that was one of them. So A is a unit, a multiplicative unit in Z mod n. It has a multiplicative inverse if and only if A and n are relatively prime. So if P is prime, so now let's prove the actual thing. So Z mod n, so n is prime implies that for all A, in 1, 2, n minus 1, right? The different classes in Z mod n, right? Those are representatives for the classes in Z mod n. We have that A and N are relatively prime. Right? Certainly, if you have a prime number, and then which I'm calling n now because that's just general notation. Later on, it will be p. And you take any number 1 through n minus 1. Certainly, it's relatively prime to n. N has no divisors other than 1. Right, and so the greatest the GCD of that number and n is 1. So n and n are relatively prime, and so this implies that A is a unit. And so this implies that the group of units in Z mod NZ cross, right? This set of units of elements which are invertible is exactly class of 1, class of 2, class of n minus 1, which is precisely, say this way, Z mod NZ minus 0. All non-zero ones are invertible. Okay, so that tells you precisely that it's a field. Now let's go the other way. If Z mod n is a field, so Z mod n is a field, implies, right? I mean, it's exactly the same argument the other way. It implies that if A is in 1, n minus 1, then A and n are relatively prime. Right? In other words, n has no divisors. Right? There isn't anything between 1 and n that could divide into n other than 1. Because if there was, that element would not be relatively prime to n. There would be a GCD which was greater than 1. Right? And so this is exactly the same as saying that n is prime. So just spelling that out, right? If no number less than me divides me other than 1, then I'm a prime number, right? Okay, so so that's a simple basic fact from algebra, maybe one of the basic ones. And so that says that we have a large supply of fields, some of which are even actual finite fields. And the great thing is that linear algebra works over them exactly as it should. Okay. Oh yes, right. Great. Let's talk about one more really interesting example, which is polynomial rings. Okay, so let me give you one more example. In the commutative, I'll just do it in the commutative case. And this is going to provide a great stock of examples moving forward. So polynomial rings, I'll stick with the commutative case here. So let R be commutative, unital as always. Yeah, as I said, rings are unital unless I specify otherwise. So let R be commutative, unital. So we define Rx to be the set of sums a0 plus a1x plus a2x squared plus an x to the n. Okay, so this is a totally formal thing as of now. So Rx is a set, and the set is the set of elements which look like, they're just expressions, formal expressions, and they look like a0, a1x, a2x squared. Okay, and now I'm claiming that this is in a ring. It has an addition and a multiplication. Okay, so how do we show that? So let's explain how to add two of them. So a0 plus a1x plus anxn. Okay, now I'm going to give you addition plus b0, b1x, bmx to the m. What is that? Well, that's a0 plus a1 plus, a0 plus b0. I almost gave you the wrong definition of addition in a polynomial ring. And then I have to go up to the highest term. So I'm going to say an plus bn x to the n plus bm x to the m. And here I'm assuming m greater than n. You can easily modify the definition if it goes the other way, right? So you literally just add the two expressions, okay? And how do I multiply? So this is addition. How do I multiply? a0 plus a1x plus anxn times b0 plus b1x plus bmxm. Right? So how am I going to do that? Well, again, it's going to be polynomial multiplication as you're used to it. So against each, it's going to be a sum of a bunch of things with powers of x, and against each thing, I add up all the terms that can equal to it. Okay? So it's going to be a0 b0 plus a0 b1 plus a1 b0 x. Okay, so what is the term next? So I'm going to give you the typical term. What is the term next to x to the I? It's a, j, and bk such that j plus k is I. So the general term is the sum j plus k equals I, aj, bk, x to the I. Like that. All right, so it's the sum over all those terms. And you can easily verify that this is itself a commutative ring. Okay. So if R is the real numbers or the complex numbers or something, then these are polynomials in the usual sense that you're used to. So they're very important. They're extremely important. Okay. Yeah, very good. Oh yeah, and he also talks about the group ring. This is a good book, you guys. I like it. So let me give you a few more examples here for this lecture, and then maybe we'll stop, and then over the weekend we'll post some more short lectures on rings. Let me give you another really nice example. Group rings. So let G be any group. Right? Then I want to consider, I can make a ring. It's kind of similar. It's going to be a formal linear combination. So then ZG is the set A1, G1 plus A2, G2, AR, GR. So again, as in the polynomial ring, this is just a formal sum. A priori it has no meaning. It's just a set of elements that are formally written this way. And the point is that AI is in Z, GI is in G. So you literally just formally make a collection of integers times group elements, and then just formally write their addition. Okay, and the point is that the way that you then define the operations is you define sum of AIGI plus sum BIGI is sum AI plus BIGI, like that. Okay, and the product, sum of AIGI, sum of BIGI. Okay, let's call this BJGJ. I think that might be better. I'm going to just kind of formally multiply GI times GJ. Okay, so right. So in other words, you need to write sum. So let's be very careful. Let's be very careful in writing this sum. So the point is that it's going to be the sum of. All right. I'll give up on my easy notation here, and I'll follow Goodman's notation. So so here I was notating I was indexing the group elements just by numbers, but Goodman here, I'm glancing at his notes here. He's absolutely right that you should denote sums by. You should index the elements by elements of the group. So let's denote this sum of AG times G, sum of BG times G. And my laziness really came back to bite me there. Or he calls it BH times H. That's even better. All right. Sorry, guys. Let me do this again. Sum of AG times G, and that's over G and G. And this is sum of BH times H, and that's over H and G. Yeah, his way of doing this is completely right. So this is the sum now of what? Well, it's going to be all of the GHs, right? So it's AG BH. So sum over G and H, AG BH times GH. Okay, but G times H is another element of the group. So this is why it's corrected to note this is the way. So he's absolutely right that what does this collapse to? You sum over L in G, and then you sum over G in G, and then you say AG, B, G inverse L, right? Because the product has to be L times L. So if you think about it, this is the same thing. You multiply this one, this is indexed by G, this is indexed by H, and it goes next to GH. This is indexed by G, this is indexed by G inverse L, this goes next to L. So it's exactly the same. So it's exactly the same thing. So the multiplication is a little subtle, and I would encourage you to take an interesting group, symmetric group in 3 letters or something, and try to write this thing out. It's quite interesting. Okay, great. All right, so this is 22 minutes, so I'll stop here. Over the weekend, I'll post the next ring theory lecture. Maybe we'll talk a little bit about ideals, prime ideals, some other fun stuff. Several of you have asked me about the plan of the course. Probably you will not hear this before this announcement goes up, but at any rate, I will send an announcement about the plan and more details about what's to come. So there'll be lots of communication from me coming up. Don't worry about that. Okay, good to talk to you guys, and I'll talk to you again very, very soon. Another video will go up this weekend for sure. Okay.